All right, welcome to a new day. This time we're going to learn how to build a computer, which is very exciting. We've so far just been talking mostly about programming, but now we're going to talk about like how to build memory, like how does that work, which is going to be really, really cool. Okay, so I do want to sidetrack us for just one slide, if you will excuse me. I want to go and review that sysinfo syscall example from last time, because the more you see it, the more it'll make sense, and that'll help you with your lab too. So I think it's worth it. So we made that sysinfo syscall. That was syscall number 179. And if you go to the man page for it, to make that syscall, you needed, first of all, to pass along a pointer to a struct sysinfo object, a place in memory with enough room for one of those, and the syscall will fill in that object for you. And here's what a struct sysinfo looks like. So we needed to figure out, like, how big is a struct sysinfo? And then the pieces that we wanted to extract were the uptime, the total RAM, and the free RAM. So we also needed to figure out like how big is a long, because that'll be the same size as unsigned long, and we'll have to like read into that when we do our load instruction in assembly, and so that was also important. And so what we did, right, was we made a little test C file to get all that information for ourselves. We made a struct sysinfo object called test, and the header that we had to include was this one that defines that struct for us. And then we can use an operator in C and C++ called sizeof. And so we asked for what is the size of this test object. It's like 112 bytes or something, right? Don't quote me on that, just rerun the program. And then we asked for like how big was the uptime, for example, and that'll tell us the size of a long on our machine, which is good. And then we wanted to know offsets, all right? So like how far away was total RAM from the start of the struct sysinfo object? How far away? So like here's the address of the total RAM, and here's the address at the start of the sysinfo object. And we just subtracted the two and printed that out. I think it was 32 bytes away, yeah? And so with all that information, we were then able to go to assembly. All right, so if I scroll over, here was our assembly file that we built. And so we made a main function, beautiful, and yeah, we were gonna call printf, and so we need to save the value that we need, or we need to save the address that we have to return to. That's in LR right now. We're going to clobber that every time we do a BL, and so we had to save, like, where does main need to return? We save that on the stack by making space on the stack, okay? So that's how we did that, and then we made the syscall. There it is happening. And we gave an address in the data section right here called sysinfo struct, and that was enough space for a sysinfo object. And that was like our 112 bytes or whatever it was. And then that gets filled in by the time this syscall returns control back to our program, back from the operating system. And then with help from our little helper C program, we figured out like what were the offsets that we need to read into. And we learned that a long in our machine was 8 bytes long, and so we want to read into X registers. So let's get the sysinfo struct's address, let's dereference it and read 8 bytes from the start. That's our uptime, right, because that'll be a long. Perfect. Every long is 8 bytes. And same with unsigned long. So 32 bytes away from the start, read 8 bytes, and that's our free RAM. Oh, sorry, that's our total RAM, excuse me. 32 bytes from the start. And then that total RAM took up, as it was a long, it also took up 8 bytes. And so 8 bytes after that, so starting at address 40, read 8 bytes starting at there, and read that into another X register. Okay, and that'll be our free RAM. And then we have a bunch of longs to print out. I don't know why uptime actually is a long and can be negative. That's interesting to me. It might have to do with like time zones, because sometimes you have like what's it called? Like maybe the time changes and now it's been your computer's been running for negative amounts of time if the time just changed or something. I have no clue. But yeah, we're just gonna print them all as unsigned longs and hope for the best. And yeah, so to call printf, remember, the first arguments go in x0, x1, x2, and x3. And so we got to get the address of that format string in x0. We did that. And then the rest go here in x1, x2, and 3. And we took care to place what we wanted there already, which is perfect. Okay? So we make the call to printf, which clobbers LR. So good thing we saved it, because now we know where to return to as main still. And then it's our turn to go back. All right, so main gets to return now, so we're going to return 0. We place our return value in W0, or X0 if it was a 64-bit value. And then to return from main, we better reload our old LR, because that's where main needs to return to. That's like the address of where we were in the underscore start label that was generated for us by the compiler. And yeah, make the stack go back to normal as it was before we messed with it. And yeah, then return to whatever was in LR, and that'll eventually stop our program. All right, so that was our sysinfo example, and I hope that makes a little bit of sense to you still. All right, so yeah, that should help you as you're doing your own thing. And so what we kind of learned was like, all right, a struct sysinfo object. We learned how big it was. Yeah. And like if this is where it began, like if this was its starting address, address X, we knew that the uptime started there. That's what we determined. And then starting at the starting address plus sorry, not 16, it was plus 32. It was total RAM. I think that was all lowercase, right? And then plus 40 was their free RAM. And then there was plenty more after that. This is not to scale. Okay, so maybe that's good enough. But that's kind of what we wanted to picture in our minds, and now we know where to load from. All right, so that's kind of how that program worked. And yeah, let's move on now to building computers from logic gates. So yeah, let's talk about these guys. If you've taken 26, you've definitely seen logic gates, but potentially if you have not, you haven't seen them yet. So let me teach them to you. So yeah, we're going to talk about how to build like a physical circuit right now. And so every circuit that we build has some like wires with electricity coming in and like wires with electricity going out, and it as this is a computer science class, those circuits are computing something. There's always a concept of like we've got inputs going on, outputs, wires, and it's voltages that are being sent and received. So yeah, every piece, every diagram that I'm going to make for you has input wires coming in with like numbers that we care about or Boolean values that we care about, and yeah, and then they also output something. So each individual wire holds a single bit of information. It's either passing along high voltages, so a 1, or low voltage, a 0. All right, and that stands for, of course, true or false. And yeah, it's really deep down in electricity land, a high voltage or a low voltage that we're passing. And so yeah, just kind of think of these things called logic gates that I'm about to describe to you as just kind of black boxes. Eventually, we're gonna like abstract away. We're gonna make like it's like the circuit level of a function almost. We're gonna put a bunch of logic gates together, and then that'll be another box that we know how to build now. All right, we're just gonna make boxes within boxes essentially, and that lets us combine things and zoom out. All right. And it's all about abstraction. We want to get to a higher level of abstraction and put together a bunch of high-level circuit boxes, and that will correspond to a computer, which is great. Isn't that cool? So all of my diagrams are going to look like this. Like you got a bunch of inputs, which are a bunch of wires coming in. Like maybe you send a 0 along this wire, 1 here, a 0 here, 1 here, and like those get fed in to other places. So like these guys go here, and then you've got wires coming out of there somehow, feeding in, going to other places, doing who knows what, coming back together, and like eventually outputting stuff. All right, that's essentially at a high level what our diagrams are going to look like. Okay, so with that, let's get started. So yeah, let me teach you about the AND gate. All right, so an AND gate looks like this. This is how we draw it when we're drawing circuits. It kind of looks like the bullet from Super Mario. Okay, and yeah, these are the inputs, this is the output, and its job is to compute the AND of the two inputs, so the logical AND. So it's essentially computing X ANDed with Y. It's multiplication in a thing called Boolean algebra. Just wait till 26 if you haven't taken it to fully understand that, but it's like you can think of it as doing that, or it's like doing bitwise with 1 bit, however you want to think about it. All right, so like if this is an AND gate, and you feed in a 1 and a 0, the output is of course going to be a 0, because true AND with false is going to be false. As long as there's a false, it's bringing everybody down, right? The only way for an AND gate to give back true, a 1, is if both inputs were a 1. Okay, I hope you see that, and I hope that makes sense. So the AND gate is performing logical AND, and this is the symbol for logical AND in mathematics. All right. So, of course, there's an OR gate as well. An OR gate looks like this. It's a bit more sleek, maybe. I don't know. Got more curves to it. And it takes two things and it outputs the OR of those two things. In Boolean algebra, a type of mathematics, it's the plus operation, but to us computer scientists, we think of it as like, this is what it's doing in C++, or like bitwise land. All right, so OR, if you're feeding into an OR gate, what does it look like? Well, if you give a 1 and 0 now, for sure the output's 1. That's great. It's a 1 as long as there's a true coming out of somewhere. So true ORed with false is totally true. And the only way to make an OR gate give back a 0 or false is if both inputs were a 0, right? That's the only way for an OR to give back 0. Okay, so that's how I'll draw those. And yeah, if you want to negate something, you use a NOT gate, or sometimes it's called an inverter. All right, so it looks like this. It just takes one thing and spits back out its complement. That's what the bar means in Boolean algebra, but it's like, to us, it's that, or even this in bitwise land. All right, so that's our NOT gate. And yeah, for reasons that will help when you're reading the textbook, I want you to think of the NOT, the negation happening in the little dot right here, because that'll help you read other logic gates that you might read about. Okay, and that I will maybe show you later. So think of the negation happening here, and this is just like bringing along the value for the ride. Negation's happening at the dot. Boop. And so, yeah, there's only two things I need to show you with a NOT gate, because there's only two things it could do. If there's a 1 coming in, it'll negate it to a 0, so true becomes false, false becomes true. Okay? Your turn. So here's all the gates, all right? Here's a circuit with a bunch of things, all right? So what is the final output of this circuit when x is 1, y is 0, and z is 1? Try it. Oh, and by the way, this little hoop thing here is meaning like you're taking from x, you're taking x, you're like duplicating x, and it's hopping over the y wire, so it's not interfering with anything. This is still x down here. Okay, that's what that means. So this is still x. All right, what do we see? So if x is 1, true, y is false, z is true, what's gonna happen? So we're gonna OR x and y. And so we got true coming out of here, right? And then we're negating x. X was true. Now it's false coming out of here. And then z was also true. And now it's false coming out of here. So false ANDed with false, that's an AND gate, is of course false. And then we have, we still have this 1 coming down here. So we're feeding in a 1 on this wire and a 0 on this wire. So unfortunately we get false output. Or maybe fortunately, I don't know what this is trying to compute. Maybe it's important for it to be false here. So yeah, that's kind of how you follow those diagrams. It's just kind of like drawing a picture and reasoning about it. It's not too bad. Okay, so you see how I fill out my intermediate steps. That's going to help you on tests. So that answer is definitely not C. And then try to go backwards. So let's say that here is a Boolean expression that you can write in C++, right? Like x ANDed with not y, all that ORed with z ANDed with x, and then negate that. All right. So see if you can like parse all these parentheses first of all, and then draw a diagram. So like you got a wire for x coming in, you got a wire for y coming in, you got a wire for z coming in. See if you can figure out like how to use these gates, combine them to build a wire coming out here that is the output of whatever this was. All right, and that's going to be a very powerful thing that we can do with these gates. Okay, and these are real things. Like if you ever take a computer engineering class, you might be working with physical circuits that correspond to AND gates, OR gates, and NOT gates. So yeah, isn't that fun? So let's see. Let's do this one. Let's do this one first. We have to OR it with all this. So I guess I need to focus on those two things first. Let's do the x ANDed with not y. I've got x already. That's fine. Let's negate y then, because I need not y. So I'll get not y right there. So now I have coming out of here, this is not y. And then I need to AND it with x. Okay? So my AND gate looks like that. bring it in, and now coming out of this AND gate is X ANDed with not Y. All right, and let's do the same for this one. I need Z ANDed with X first. Cool, so I need an AND gate over here. Z ANDed with X, so put in the Z, I need to AND it with X. So let's take an X, duplicate this wire, hop over the Y. That's cute how the diagrams do that. Hopping over the Y, and then going into there. And now coming out of here is Z ANDed with X, or X ANDed with Z, the order of operations there, doesn't matter. So that's Z ANDed with X, and then I need to negate that, right? I need to negate whatever the output was there. So I'll send it through a NOT gate, or an inverter. Let me make that a little bit more pretty. And so now coming out of here is the negation of Z ANDed with X. All right, so now I got this piece and this piece. And the last piece of the puzzle is to OR the two sides. All right, so I'll use my handy dandy OR gate to take this and then this wire holds the answer. Okay, and I think that is what you do. So I hope that you got that, and yeah, the more you practice, the more it'll make sense. But like, this is building a physical circuit. You could buy all of these parts and hook them together like this. It is possible physically to do that. All right. I taught you about exclusive OR. Remember that one? It's XOR for short. So it's short for exclusive OR. And so it's like regular OR. I'll just do the example again. So let's do the truth table for exclusive OR again. So A exclusive ORed with B looks like this. So true, true, what are all the possibilities? True, false, false, true, false, false. So it's like OR for all these guys. It's like, all right, true, true, still false. But it disagrees with normal OR, which is also called inclusive OR for the double true case. It considers that to be false. So exclusive OR is all about, like, are they true? Do OR is one true, but is that one thing true exclusively? So you can't have both being true. If they ever match, it's false. But if they like disagree, one's true, the other is false. Exclusively, one is true and the other is false. Then the answer for the exclusive OR gate is true. All right. So this is the gate that you use for exclusive OR. You kind of draw a normal OR gate, and then you put another slash here, another little line. All right. And so yeah, this is like the bitwise operator. And technically there's a logical operator on Booleans that is exclusive OR. It's essentially, it's equivalent to the not equals to operation, isn't it? So that's how you can do exclusive OR on Bool values in C++. So there's that. And then, yeah, now I get to show you like why I told you to consider the negation happening right there for the NOT gate. I want to teach you about NAND and NOR. All right, this is some fun ideas. So, all right, let's do it. So NAND and NOR are their own logic gates. You can have just NAND, you can have just NOR, but we like to think of them as a combination of the gates that we know, all right? But they're made differently. They are made like you can just make a NAND gate by itself with some transistors, all right? You don't have to combine them in this way, but as humans, let's think about it this way. So a NAND gate performs the NAND operation on two things, so X NANDed with Y. That is equivalent to, kind of read it like this, first do the and then negate, all right? So do an and on X and Y, so X and Y, and then negate it with the not operation. So that's what NAND does. It's a combination of these ideas. Do an and then negate it, and then we draw the gate like this. See that? So that's going to help you, like do the and then negate it. Right? So that's a NAND gate. And then there's also a NOR gate, as you would expect. First do an OR, then do the not, and you draw it like that. Okay? So the cool thing about NAND and NOR is that they are both what are called functionally complete, all by themselves. All right? So you'll have to take CSCI 26 if you haven't already to fully understand this. But the idea is, the idea of functional completeness is, let's say you have a bunch of input wires. X, Y, Z, P, Q, as many as you need. 1 million maybe. That's totally fine. And you write down all their possibilities. Like, all right, they could all be true. They could, like, They could be some weird combination of true and false. You write down every possibility, and then you write down what the output should be for your particular operation that you want to perform on these wires. It's like, I want it to be true in this case, false in this case, true in that case, ... for every one of the million possibilities that it could possibly be. Like, this is the output I want. And then there is a way, using just NAND gates, to build this output based on these inputs. That's what functional completeness means. You can just use NANDs to produce the output of any truth table you care about. And same with NOR. NOR is also functionally complete, so you can just go to Logic Gate Costco and buy in bulk a bunch of NORs, and then your entire, whatever you want with the wires, you can build the output how you like it. All right? So you can make, the idea here is you can make a whole functioning CPU, because that's all these logic gates are doing. Eventually, you can use them to build a CPU out of just NANDs. And that's cheap, because you can just keep making a bunch of those. Go to Logic Gate Costco and get things on sale. So yeah, that's what that means, and that's why these are important. But I'd rather teach you in terms of and or not, because as humans those make more sense to us. But everything you can do with and or not, those three together, by the way, are functionally complete. You can build whatever truth table you want with just and, just or, and not. Or sorry, not a combination of and or and not is what I mean. And that's how we'll think about things. But in actual CPUs, we like to just use a bunch of NANDs or just use a bunch of NORs. Okay, so with that, we started actually at a high level. What is a logic gate? It's these things. It's this magical box that does these operations. But how do you build those magical boxes? We want to zoom in now. So each logic gate is built up using one or more transistors, things called transistors. And yeah, here's kind of what a transistor looks like. You think of it as a box, right? A transistor is, to us at least, to us non-engineers, it's a box with three inputs / outputs, right? There are three things. So there's actually a bunch of different kinds of transistors, and they call those three inputs or outputs different things. I'm going to use a certain kind of transistor, all right? This kind, with this kind of diagram, all right? So to us, there are three pieces to a transistor. That's all I care about you knowing. There's an input wire called a base. All right. There is an input wire called a collector. And then there's an output wire called an emitter. So those are the orientations of those. And by the way, if you ask most people, in our field, they would all agree that the transistor was the greatest invention of all time, of mankind, because it's been able to make computers small for us, and so we can significantly improve everybody's quality of life. All right, so transistor, a lot of people believe that it was the greatest invention that man has ever made. So it's kind of cool to learn about them. So yeah, those are the three pieces, and they can do some cool stuff. You can make a guitar amplifier with a transistor. But in computer science, all we care about is that transistors can function as an electronic switch. All right. So if you, it's like this. Here's a little switch in here, and by default it's off. So if you send a 0 along into the base, it's going to control whether this switch opens or closes. What you send to the base controls whether the switch opens or closes. So if you send a 0 into the base, if you send a 0, that will keep the switch open. All right, it looks like this. It's not letting things come through and connect the collector and the emitter. They are cut off when it's a 0. All right. If, however, you send a 1 instead, let me draw that a little tighter like that. If, however, you send a 1 along the base, that will close off this circuit. All right, and the switch will be closed, and power can flow through the collector and the emitter. So by sending power, you can control whether or not this wire is open or closed, sending its own power. I hope that makes sense. It's functioning as an on-off switch using nothing but electricity. All right, and cool things. All right, cool metals packed on top of each other. So yeah, that's all that a transistor does. It functions as an electronic switch that can be turned off and on really, really quickly. All right, faster than any human can flick a real one. All right, so yeah, so 0 input. opens the switch and the collector is cut off, the power cannot flow through this way. If you input a 1, though, that closes the switch and the collector is connected to the emitter and power can flow in that direction. All right? And so this is kind of what a certain kind of transistor looks like. You got 3 pieces, and here's kind of how the real drawings are done when this kind of transistor is in a legitimate circuit diagram. But honestly, all I really care about is you understanding this and the logic gates. All right, we're not going to go too deep. If you find this stuff interesting, definitely consider taking a computer engineering class. So yeah, all that I'm trying to get at today is that logic gates are made up of transistors. That's how we build our NAND, our NAND, our NOR, our AND, our OR, and our NOT gates. Okay, so I'm going to teach you how to build an AND gate for this slide. All right, but I do want to warn you, when you do decide to take a computer engineering class, or if you already have, do not worry. My transistor diagrams are incorrect by design. All right. They're very incorrect from a real engineering point of view and also from a physics point of view. I am teaching you computer science. I do not care about those other things right now. They are morally correct, though. What I'm about to show you more or less is correct, but I'm sweeping a lot under the rug. All right? You really have to deal with like resistors and getting the exact voltages right. I don't care about that right now in this class. All right? Take a physics class, take an engineering class if you care. But let me show you how to use transistors and line them up to make an AND gate. All right. So let's say that I would like to AND together A and B. There are 2 inputs that I want to compute the AND of, the logical AND of. Okay. So here's kind of how it works. All right. There's a bunch of moving parts. So I've got the A, right? I've got the A wire coming in. I've got the B wire coming in. High or low voltages, and I want to AND together A and B, all right, using transistors. And so here is the secret. I've got a transistor here and a transistor here, and both A and B are going and functioning as the base part. All right, they're feeding the information in. They are to the base. All right, that's what A and B are doing. And then the collector and emitter look like this. We're going to have a source of always 1, always truth, like power. We're going to have a power source. Here's our battery or something. Here's the wall outlet. So I'm going to have a 1 coming in this way, collector, and remember, like, this is a circuit, like by default it's open or closed. Same with this one. I'm going to have the emitter of A be connected to the collector of B, and then I'm going to have the emitter of B be connected to a 0 wire, a wire that is like, this is the ground in your circuit. And then I'm also going to hook into whatever's coming out of here, and that will be my output. All right. I understand that this is kind of confusing when you first see it, but we have like a source of 1, a source of always true, a source of always false, and I'd like you to pretend that 1 always overpowers the 0. Right now, like if the circuit is cut off, the 1 cannot reach the output, but if it could, it will overpower the 0. It wins in a fight with the 0. Okay. That's the first thing I want to say, and so yeah, let's talk about this. I guess I do have Tinkercad. I can maybe open it and show it to you. But yeah, let's at least start with this. So pretend that the 1 overpowers the 0. And so let's pretend. If there is a 0 anywhere, if A or B, either of them are 0, do you see how one or the other of these circuits is going to be closed off, right? So if A is 0 and B is 1, like sure, this goes through, but the 1 is still not going to jump over everything. This is still like it can't get from here to here. All right. So as long as one of these is a 0, the 1 cannot reach the output. It cannot win in a fight. And so the 0 is going to take precedence. The 0, we're going to see false in our output of A and B. And that's exactly what we want. All right. If, however, all right. So yeah, if it's a 0, the 0 is going straight to the output because the 1 can't like hop over these guys. At least one of those circuits is going to be open. However, if they're both 1s, right? If we're feeding in a 1 high voltage along both of these, we will close off each of these. And that will allow the 1 to flow through to our output and beat the 0 because it overpowers it, we say. That's what we're pretending. And then we see a 1 in our output. So that's the one time we want to see true, right? True and with true should be true. Any other time it's false. Does that make sense? Like that's the secret. That's how logic gates work. That's how you form them with transistors. So Tinkercad. there's a cool website that I'll show you more of later. Dun, 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 I am an educator. I think I signed in with my email. We'll find out. Dun, dun, dun. Cool. So there's a fun little website called Tinkercad, and I've made an example diagram of a AND gate using this kind of transistor. It's called an NPN transistor. And so let me click here. And so you can make virtually this kind of circuit, and I'll show it to you. The real deal, I get to show it to you now. So there's, like, here's a power source, here's some wires coming in, here's one transistor, the other transistor, and I've got these two switches that can either go on or off, right? And then the output is a light. The light is on if it's the output's true, and then it's false if it's off if it's false, all right? So here's my little simulation, and apparently the switch to the right is on. And so if it's 0, 0, light's off. All right, we're combining these things. You can see there's a collector, base, emitter. They're all working. You do need some resistors, though. These things are called resistors. If you haven't seen those before, they're necessary so that we don't blow up our output. And then, all right, one ANDed with 0, still 0. All right, 0 ANDed with 1, still 0. Only if they're both true does the light turn on, and that corresponds to true output. All right. So isn't that fun? Let me know if you want the link to this. I'll give it to you so you can play around. But that is that's the secret. All right, that's how you can design an AND gate for real. And so people have gotten really good at making these things, and they've made them very small. All right, super duper small. So all right, this is how you make an AND gate. OR is very similar. See if you can. All right, I'll show you the answer on the next slide. See if you can, using the similar kind of diagram, like here, let me recreate it for you for just a second. This is an AND gate, right? But with the same idea, an A, a B, a 1, a 0, an output. See if you can hook together two transistors again in a different way to make an OR gate this time, all right? How do you get an OR? How do you make sure it works? If any of them are 1, the output's a 1. See if you can figure it out. And it's helpful to think about this kind of stuff, because this is the backbone of everything, all right? Helps your critical thinking skills for sure. So, all right, let's have an A, a B, and as usual, these both will be coming into a transistor here and a transistor here. I'm going to offset them for a reason. Like here's a 1. Here's my 1 source coming in here as it was. A is going to go to the base. B is still going to go to the base of this transistor. Here's my little circuit by default with the 0 open. The secret is, here's my output over here, and here's a 0. The secret is I always want the 1 to go through if either of these switches is closed. So if A is a 1, I want a way to get a 1 into that output. All right. So let's force that. All right. Let's force that to happen here. That wire needs to go right there. So if there's a 1, this will be closed, and then coming along out of here, I want to take that and have it go straight to the output. Does that make sense? That's what I want to do here. And then we'll figure out where this goes in a second. And then same for B, right? If B is ever a 1, this gets closed. So I want a way to get the 1 into here. So let's boop, hop, boop. So if B is ever closed, again coming out of here, I would like to go and send that 1 into the output. Hook it in. All right. See how if B is a 1, this will close, bringing the 1 into the output now. Cool. And then finally, if they're both false, if they're both open, I need a way to get 0 always. All right. So here's how I'll get 0. I'll have my 0 source here, and if they're both closed, I'll have a way to always have a 0 get in there, and then I'll feed this here as well. All right. So both of these. So now you see that if they're both closed, there's a couple ways for 0 to get the output. All right. But otherwise, if any of these work, right, they shut themselves, then the 1 makes its way out of here, always to the output, overriding the 0. All right, it wins in a fight. So that's kind of in a nutshell how you'd make an OR gate. I hope that makes sense. It's give each of these a chance to bring that 1 into the output. So it looks a little wonky, but that's kind of how it works. Here's the real way to do it. You need some resistors secretly to do these things, and that's kind of how we make 0 when in a fight with 1 anyway. So here's the real way, using the real kinds of diagrams to make an AND gate. You see that it's pretty much the same, like they're in series here. And you got the same weird kind of stuff where the 1 gets to win out. The 1 gets to win out positive voltage out there. All right, so that's kind of how that looks. So yeah, this is positive voltage or a 1, and then this is your ground or a 0. That's how these diagrams look. 0, 1, and then here this was the OR, and this is how you make a NOT gate, by the way. So here's your positive voltage, here's your ground, your 0, and this one's a bit weird. This one you need to know more about physics to like understand why the NOT's going to work properly in this way. So you kind of like put the transistor in a weird place. The secret is that in the NOT gate, I'm not going to test you on any of this. This is just for your knowledge. In the NOT gate, you actually want the 0 to overpower the 1. All right, and the way you get that to happen is you put the resistor right next to the 1, rather than how it was here. It was next to the 0. So that's more than I want to talk about. You'll learn more about this in a physics class for sure, if not a computer engineering class. Okay, so yeah, that's the secret. That's how you build our stuff out of transistors, and we're not going to zoom in any further. I'm not going to teach you how a transistor is made. It's a cool, fancy process, but that's beyond us. We don't care that much as computer scientists. We just get to use them, all right? But transistors build logic gates, and logic gates, if you have enough of them, you can build a CPU, all right? And so that's crazy. An important part, of course, of a CPU is memory. So I need to teach you, how do we build memory out of logic gates, which are themselves made up out of transistors. So we're already doing that thing that I told you we were going to do, right? We're already using abstraction, because instead of drawing weird transistor diagrams, we're just drawing this pretty picture that looks like a bullet that's our AND gate. It's doing it for us, all right? So we're zooming out. So we're going to zoom out further now and talk about latches and flip-flops. So this will be something you read about in your book for sure. Did I give you any assigned reading, actually? I did not. So I guess I will eventually. But your book talks about this for sure. Maybe I already assigned this chapter. But yeah, let's talk about this first thing. So latches and flip-flops. All right, these are two words that mean very similar things. People usually consider them to be synonyms. And I'm going to teach you about latches. All right. They both are memory. They're both a type of memory. They hold on to data, all right? They hold on to data, a single bit of data, and you can, of course, chain them to store multiple bytes. And yeah, they flip to 1 and 0. They get to hold a 1 or a 0 at the request of you, the person programming these things, making the memory, setting the memory, all right? If you were the CPU, for example. Some people only say the word flip-flop when there is a clock signal involved. All right, that's kind of what I've figured out over the years. So a clock signal looks like this. This is actually the other piece that you need to build a computer. You need a bunch of logic gates, and you need something called a clock signal that oscillates really quickly between 0 and 1. And so it stays 1 for a while, and then it stays 0 for a while, and that's how your CPU can know that time has passed. Because like if you keep sending power, a 1, always, the CPU won't be able to understand that, okay, I need to pass this information along. It doesn't know that time is passing. But if you go between 1 and 0, it can it's like a clock tick, essentially. And so that's why we call it a clock circuit. All right, so this is a clock. And some people say that, all right, this kind of memory stuff only works, and we only call this type of memory a flip-flop when the clock is involved. All right, so I'm going to teach you about latches. Let's pretend, let's not even worry about clocks right now. So it's called an RS latch that I'm going to teach you. That's the type that we learn about in our textbook. It is a way of using NAND gates, at least, to make memory. There's other ways, but we'll use NAND in this example. All right. So here is an RS latch, and this holds memory. All right. It takes some inputs to potentially set the value that we're holding on to, and then another value that's going to tell us when we want to pass along a new value, this is what we put in, I want to store this 0, I want to store a 1. You have to bring that into one of these RRSs. So we'll figure out which one in a second. And then the output, there's actually two outputs from each NAND gate. There's a thing there's the Q value, and that is the thing we're actually storing. But just for free, we also get its negation if we wanted to. So like if we were storing a 1, and the 1 would go here, and this would always be guaranteed to be a 0. Or if we were storing the bit 0, we would have the negation of this down here if we needed it. So we always have its negation as well. But we look at this, like this is the value we're really storing, all right? And so here's the NAND gates, and you've got 2 inputs, and then also here the outputs being fed back in as inputs to the opposite NAND gate. So that's called a feedback loop. And that's a little weird. So weird electricity stuff is happening inside of this latch, all right? And it does work. It is well defined to do this, and let me show you how, all right? There is one thing that is not allowed, but the others are allowed. So, all right, here's how you use memory as an RS latch. All right, here's how you set it and unset it, or have it keep storing a value. All right, so if R is 1 and S is 1, if they're both sending 1, all that means is I'm not changing what's in the memory right now. I'm just keeping this circuit powered to keep on holding on to whatever it was holding on to, all right? So let's say it was holding on to a 1, all right? Let's say that it was holding on to a 1, that's in memory right now, and I want it to keep holding on to that one. I have to keep feeding power into both R and S, high voltage, all right? And let's watch it work. Let's watch both of these NAND gates do weird stuff, all right? So a 1 comes in, and a 1 comes in. We know that there's a 1 here, that's what we're storing. And so that 1 is being passed here to this NAND gate. So we got the 1 ANDed with 1 and then negated. So that makes the output 0. That's perfect. And so that's still the opposite of what we're storing. That's the 0 there. That's perfect. That is correct still. And then this 0 is also being fed into here. So 0 NANDed with 1. So 1 ANDed with 0 is 0. Negating that becomes a 1. And so we keep on having the same value held there. Nothing is changing. That's how we keep it storing the same value. Those weird feedback loops create memory. Isn't that weird? 2 NANDs make memory. All right, so that's how you keep storing your current value. And then, if you ever want to set your RS latch, if you ever want to change what you're storing, if you want to store a 0, here's what you do. You set R to 0 and S to 1. All right, you set R to 0 and S to 1. If you want to store a 0, and so the R and the S kind of stand for set and reset. It's like we're setting the not Q to something, or we're resetting the not Q. It's kind of how you think about it. So yeah, if R is 0 and S is 1, here's a diagram of that. Dun, dun, dun. Let's see if I can zoom in a little bit. Whee. So R is 0, S is 1. We don't really care about what we're storing right now because maybe we're storing a 1. We want to change it to store a 0, right? So we're changing stuff. So the 0, we feed it in here. Everything else was the same. Nothing has changed yet for everybody else. But that's going to cause this NAND to do something different, right? It's going to, 1 NANDed with 0 is now 1, which feeds in the 1 to this NAND. And so now it sees 1 ANDed with 1, 1 NANDed with 1, sorry, which is going to be, the output will be 0 there. And this 0 is being fed back in. And that actually keeps it a 1. It was already 1. It's keeping it a 1. And so that's reset everything, all right? So that changes the output, right, to 0. That's the stored value is now 0. And if we just keep sending a 1, I encourage you to try everything out. But everything, it's in a steady state now. It's going to keep having a 0 come out here and a 1 come out of here. Everything's fine. So now that's how we switch to what value we're storing. And you can do the same thing. You can... all right, if we're storing 0 now, you can make it store 1 again by setting R to 1 and S to 0. And I encourage you to follow and kind of do this kind of diagram yourself. And there is one state that you can never let your RS latch be in. That's when they're both 0, all right? So if you do it like this, if you set them both to 0, then weird things happen. If you set them both to 0, that makes them both output 1 here, which doesn't make sense. This is always supposed to be a stored value, and this is always supposed to be the opposite of the stored value, and so that messes everything up. So we just make sure this never happens, right? Always somebody's a 1, all right? And if you want it to keep storing the current value, they're both a 1, okay? So that is an RS latch. That is how memory gets made. It's really, really cool. Read more about it in your book. And let's abstract. All right, we know how to make an RS latch now. We can just have a box for one of those. All right, so let's combine. let's make what's called a D latch to make this a bit easier on us, the CPU implementers. All right. So this is called a gated D latch. It looks like this. It's made up of an RS latch. Here it is, as well as some other pieces. All right. The inputs are different now, and these inputs make more sense to us as CPU manufacturers. All right. So a gated D latch makes sure, first of all, it's going to give us some safety here. It's going to make sure that R and S can never be 0, because it's taking care of like what is going into S and R. All right, so that's important. And yeah, there's two pieces to a D latch. There is a data piece, and there's a WE, which is short for write enable line. All right, so there's a data input, and there's a write enable input, and those are both being fed in some weird combinations to S and R. All right, they're going to take control. And this makes more sense to us. So this is kind of how it works. If you ever want to change the value that you're storing in your latch, in your RS latch, you will send a 1 along write enable. So if you ever send a 1 here, that means, all right, whatever's coming into data, I want you to store that. So like put in a 1, it'll store the 1. Put in a 0, it'll store the 0. Does that make sense? So write enable, when you send that high, we say, if you input high to write enable, which is the 1, right, high voltage, then it will take whatever D was and store that inside the latch. All right, so that's that. Definitely try that out yourself. Watch it work. And whenever write enable is 0, watch how there's a 0 coming in to both of these guys. There's a 0 coming into both of these guys, and it doesn't matter what D is. Could be question mark. There will always be a 1, right? Because ANDed with a 0 is 0. Negating that becomes a 1. Same for here. There will always be a 1 coming in to both S and R, and that's going to make sure it's always holding on to its current value. And so that just makes our life easier. All right, so now we can use these D latches, and it makes it it makes sure this RS latch is always going to play nicely with itself. Okay, so yeah, when write enable is 0, then that's going to force both inputs to the NAND gates to be a 1, and that will make sure the latch just keeps on holding on to the right value. All right, and so now if we want to store like a bunch of bits, like we want to store 64 of them to make a register, for example, we can zoom out and like here we know how to build this and zoom in if we ever wanted to, but we can like chain a bunch of gated D latches now, and that is the beauty of it all, right? So now like I have this box that I know how to make if I ever need to, but now I can chain those at a higher level of abstraction. Isn't that cool? And so yeah, deep down there's that RS latch inside of there. I can use that, and deep down inside of those are NAND gates, which contain transistors. We can go as deep as we want to, but it's better to zoom out. All right. So this is legitimately how you build a register. Isn't that cool? Because all a register is a bunch of D latches hooked up together. You have a very fat wire. Let's pretend we're making a 32-bit register, so like a W register or something, and we just need to combine them all and store 32 bits. Does that make sense? That's the goal. We only need one write enable, like it'll either be 1 or 0, just one wire for that, because if the write enable is ever a 1, we want to store to each individual one of those 32 bits. Does that make sense? It's like that's how you build a register. And so this is just, it's really meant to mean a bunch of 32 wires. It's a bus, all right? So that's how you do it. You build bigger and bigger boxes, all right? So these are a bunch of latches hooked together. This is each piece of data being fanned out there, each bit that we want to store in each latch, and then we either want to write or not write. If we want to like do for example, if you want to do like a move instruction, move into W0, W1 or something. It's like go and read from W1 and send it into W0. So set the write enable high. This is coming from W1, this information. And then if anybody ever asks for W0 again, like they can read from these wires. Does that make sense? Isn't that so cool? We know how to build a register now. And of course for 64-bit registers, which are what we really have. This is kind of just an abstraction. But in your book, it's doing 32-bit stuff. So we really have X0 and X1. We're just using pieces of those, but this is how you build a 32-bit register, and you can just add 32 more D latches to build a 64-bit register, right? And now that we know how to build registers, we can abstract. We can zoom out to those boxes and put a bunch of those together, because we know that inside of each of our CPUs, there's a bunch more, right? There's 32-ish registers for us. And so that's kind of the game that we're going to play in these kinds of lectures. We're just going to keep on making boxes out of smaller boxes, and we keep on zooming out. And that is the beauty of abstraction. Isn't it great? So yeah, I think that's what I wanted to say for this lecture. Not as much programming, but still very important stuff. So yeah, I think that's all I wanted to say, and I will see you in the next one.